Hey, Fiveable. It is 1 hour and a half before you need to log in and actually take this awesome exam that you are all 100% prepared for. Even if you don't think you are, you are. You are here, and that means that you 100% have to be able to be ready because you guys have come on a lot of these Fiveable sessions. I know you've studied on your own, you've done all those kind of things. So I just want to make sure everybody can hear me really well. So I'm going to turn the chat on for approximately 5 seconds. Then I'm going to turn it back off, and I'm going to kind of talk about a little bit some things that you need to do last minute. We'll probably turn the chat on every once in a while to grab some other questions. But they did send a notification out just asking kind of some things that you want to know about. So we're going to go through some of those things. I'm going to try to help you here in the last few moments before you take the test. But go ahead and let me know, can you hear me? All right, cool. Hey, I appreciate that. All right, what's up? Okay, so we're going to disable the chat. Thank you so much. All right, first and foremost, take a deep breath. Okay, blow out, because that's what you're going to need to do. Take your time. Know that this test is more than doable, okay? I grade these every year at the big reading in Kansas City. This year, there are well over 600 teachers, physics teachers, that are going to grade your responses. So the first thing I want to tell you is this: recognize when you're writing, you should be writing kind of like you're writing to your teacher, okay? You don't want to write like you're writing to your friend or to your mom and you have to explain every little last thing. But you do need to make sure, absolutely, that you're including the things that we've talked about a lot on this channel, and that's making sure you give basic physics, that you cite evidence, that you draw things together, and most importantly, that you answer the question, okay? So those are some things that I really think you need to know. Here's the other thing that I'm going to tell you, and you'll want to make sure that you have a copy of this very handy. If you haven't printed out the AP Physics 1 equation sheet yet, I would say at some point during this Q&A session, you really should. Because if you have a printed copy, it's a lot easier to go through and look things up than having to switch screens. So I'm going to move this around just a little bit. And I want to show you a couple things about the equation sheet that are super important. First and foremost, I'm just going to get rid of just a few things here I was talking to my students about. You are not going to use anything in this electricity part at all. So if you, for some reason, think that one of those equations looks good for this test, just bear with me, don't do it, okay? The only one that I think a lot of you might go, oh, hey, yeah, I might be able to use that one, is this one that has the force of electricity in it. There aren't going to be any of these equations used, referenced, or anything else on this exam. So one thing you might want to do, if you've printed this out, is just cross this thing off, okay? Because you won't have anything from electricity on the exam at all. Now that leads us over here to the other side, where there are several things that I want you to kind of pay attention to. One of them is, you know, that at the very top, and I'm going to help you just a little bit here, these three questions are your basic kinematic equations. So these all deal with acceleration. You should know when to use these and when not to use these. The best way to know that is to look and see what's missing. So in this one, there's no position. So this one is no delta x. The second one, you'll notice there is no final velocity, so you don't have to worry about it. And then in this very last one, there is no time. So if you don't need time and you don't need to solve for it, then you're going to use an equation like this. The next section are the force equations, or we call those the dynamics equations. And those are the two equations you'll see here. The next one is the centripetal acceleration. So this is, for example, let's say I have a person and they're holding onto a string, and that string then has a ball on the end, and it's rotating in a circle. If I want to find the acceleration, the centripetal acceleration, I know the tangential speed, so that's what this v is, and I know the radius. I can square the v, divide by the radius, and that will tell me what the centripetal acceleration is. Remember that centripetal acceleration points directly towards the center, okay? Momentum is our next topic. So you'll see momentum is right here. And this is linear or translational momentum. So this is in a straight line. The second equation, remember, is for the impulse momentum theorem, or the change in momentum. Then we have energy, work, and power. So our energy here is kind of scattered. So we have the equations that you see right here. Some of these, well, these are all involving work, energy, and power, but we also have another one. And that one, for some reason, they have stuck it down here. So this is another equation for energy. And then finally, your last energy equation is this one down here. So all of these, well, it's almost your last one. All of these are your energy equations. And the reason I want to point these out is because energy is the topic that kind of holds physics together. It's like the glue of physics. And you can start and solve most problems with energy. There is another energy that you'll see, which was down here. It's not as often used, but this would be the energy between two massive objects like the Earth and the Sun. Could be between you and the Earth, but then it kind of breaks down into some other things. But nonetheless, this is the potential energy due to gravity on the Earth. This is potential energy of gravity between two large bodies. This is spring energy. Then we have kinetic energy, and then we have the work energy theorem, which just means that work and change in energy are the same. Remember, work is force times distance, and here we've got force, distance, and the cosine of the angle. Here's power. The next series of equations, there are two of them here. These are rotational kinematics. Then we have simple harmonic motion. This could be on the exam. Remember, this one's not very difficult. It looks bad, but it's really not. If I have a sine wave, well, actually, let's do this correctly. Let's make this a positive cosine wave, since we have positive cosine here. So it would come down, and then it would come back up. And we know that f is the frequency, so it's how many of these waves pass per second. T is the time. 2 pi just means that it's got this simple harmonic motion structure. Cosine is, remember, cosine starts either at the top or starts at the bottom. This one's positive cosine, so it starts here. And then x is my position somewhere on this curve. So I can find the position at any particular time by using that equation. Are they going to have you do much of that? I doubt it. The other equations for simple harmonic motion actually occur over here. And so we could link these equations together. So this is for the position on a wave, and then these are super important because this is the period of a spring and the period of a pendulum. And they're going to ask you some things, most likely, about either one, or maybe even compare the two. Remember, mass only has an effect when you have a spring oscillating. And then when you have a pendulum oscillating, it's the length that is the big deal. We also have constants, and you'll notice that the constant for the spring is on the bottom, and the constant for gravitational acceleration is on the bottom here. So the only things that we have that are going to change in each of these equations are the things on the top. So period of a spring and the mass. So if you're asked what you should graph to find out the spring constant, one thing that you'll want to think of is, well, how is this equation set up? It's set up very much like y is equal to mx plus b. But we need to think a little bit more about where our m and where our x are. The two things that can change are my y and my x variables. So for example, the period of the spring, we're going to put on the y-axis. And then if I put the square root of mass on this axis, notice what you're going to get for your m value is going to be, so your m value is your slope, and this will be 2 pi over the square root of the spring constant. So if I find the slope to find the spring constant, I'm going to need to divide by 2 pi, and then I'm going to have to do 1 over the square of this thing. So they might do something like that in a qualitative, quantitative translation. So you want to be careful that you can use a lot of these equations in that format. Then when we go back, we'll notice that we have, this is acceleration, angular acceleration, torque, and moment of inertia. And so these are our dynamics equations for rotational dynamics. Then we have angular momentum equations, and so there's two of those. One of them links torque, the other one links angular speed and our moment of inertia. Then we have angular or rotational kinetic energy. So one of the things that I had my students do on the two kinetic energy equations, since there are two of them, I put Kr here and then put Kt for translational or linear kinetic energy there. Down on the bottom, you'll notice, oops, here's another force equation. And so that one really could go with what we have up here. And I know they have a rhyme and reason for doing these things, the way that they've done them, but that is another dynamics equation. Notice that they've put it here because now they have the energy of a spring, and that also involves K, hence why they are together. The last equations that you really need to make sure you focus on for this exam is the absolute force of gravity between two objects, and that's just big G, the universal gravitational constant, times the masses divided by the distance between them squared. If you modify this equation for Earth, then we end up with our good friend, the acceleration due to gravity, which we know is approximately 9.81. Because you shouldn't be doing a lot of calculations, if any at all, you probably will not need to use 9.81 or 10 on the exam. The only other equation that is on the equation sheet that I'm not 100% sure they're going to totally ignore, although I think they're going to, is the one for waves. So remember, the two things that are not on the test are electricity and quote-unquote waves. And by waves, what they're talking about are standing waves. So maybe I have a open-ended pipe like this, and they want to know, what does the wave on the inside of that pipe look like? And so you would have to draw it, and then you'd have to do some other things. You will not need to do that on this exam. If you have a vibrating string, and so you've got all these nodes and antinodes, you will not do that on this exam. They're not going to talk about superposition and things. However, do notice down on this equation, we do have frequency, and we have frequency on this equation. Could they, if they wanted to, try to incorporate this? Yes, but I highly doubt they will. I think anything, they're going to have you go between period and frequency. And so you can use T is equal to 1 over F. So those are the things I think that you kind of need to think about when you look at the equations. The one we didn't really talk about is one that's barely hardly ever used, and that is density. And density is just mass per unit volume. Up at the very top of the equation sheet, they might put things in different units instead of meters. They might use centimeters. So let's say that they tell you something is 10 centimeters. To convert it is really super simple. You just type 10 times 10 to the negative 2 meters. So you just put whatever the prefix is after it, whatever this factor is, I'm sorry, so times 10 to the whatever it is instead of the prefix, and then you can just put meters or gram or kilograms, whatever it is that you need. Also remember the basic units that we use in physics are a kilogram, a meter, and a second. Some people say it's King Midas, and so you could think of it that way. On the front side of the equation sheet, there are certain things you will not use. You will not use the electron charge magnitude. That is part of electrostatics. Coulomb's law constant, you will not use. This is not for a spring. This is for something else. The universal gravitational constant, you will use it. And you will also use gravity. So we want to make sure that we have those. They give you some masses of some other things. They might have you find the energy associated with a proton. And so they might say a proton is moving across the surface of something or another or through the air, and they'll want you to find the kinetic energy of that proton. They could do that. They probably will not have you use these. There are unit symbols here, so if you forget, you will see those. Remember that our basic ones are right here, kg, m, and s. So probably a good thing to circle those. You will not be using ampere. You will not be using coulomb. You will not be using volt, nor will you use ohm. But everything else there, you should make sure that you're at least a little bit familiar with. The one that you might not use on this one is a Kelvin. We don't really talk about thermal energy, so you probably will not see it. Watts, you should see if you do power, and then everything else is a basic unit of some sort of thing that we use pretty often. Remember, newtons for force and joules for our good friend energy. Okay, so that is the equation sheet. The other thing you want to look at, we always use in an inertial reference frame. Assume air resistance is negligible unless otherwise stated. So they will tell you whether you have to worry about air friction. Positive work is work done on a system, so don't forget about that. The direction of current, you do not need to worry about this. And then finally, you don't need to worry about number 5. So those are the things that I think you can kind of take a peek at and kind of see. All right, so some things that people have asked for us to go through. We had asked you to kind of go through and write down some things about what is it that you want to know out of this Q&A. So the first one is how to know which strategy to use to solve a problem. Okay, here's the kicker. There are no problems to solve on this exam. However, there are lots of things that you need to explain. So let's go through and let's just kind of take a look at some sort of scenario, and let's go through and figure out how we would explain this scenario. So for example, let's say we have an incline. At the top of the incline, we have a ball. And then we know several things about this incline. We know the angle, and we're going to call that angle, instead of theta, I think what they're going to do on this exam is they are going to give them letters. So they might say that that is letter D. It probably will have a height, h, the length, and then it will have a distance from left to right. So that is kind of what they're going to do. This ball probably has a mass of little m, and probably that's about it. And they're going to say there's 2 positions, position 1 and position 2. They will then say, please write or give a statement about the speed of the object at the bottom. So describe how you could explain, so describe how you could find the final velocity of the ball at the very bottom. So now this is where I think you really need to use the basic physics. So we're going to write basic physics, cite evidence. So we're going to do that, and then we're going to draw it together, and we're going to answer the question. So I've even told my students to use B, C, D/A. You could also start with C and then do B and then do D/A. You could start with A, do B, C, and then D. Totally up to you, however you want to do it. But the first thing you want to do when you go to attack one of these problems is I would have a sheet of paper out with a pencil and or a whiteboard with a dry erase marker. That's probably the biggest thing. And that's one of the things I need to remind my students here in just a little while. Draw out the situation if they have it, and then write things down that you know very quickly. Remember, you want to be typing for about 99% of the time. You do not want to handwrite on this test. Here's why. It takes a lot more time, as you can see, for me to handwrite stuff. Then I have to take pictures. Then I have to upload those pictures to my device. Then I have to upload my uploaded pictures to the test. The unfortunate thing is, if you have an iPhone and you don't convert it from HEIC into JPEG, then you're going to have some issues because it will not take HEIC on an iPhone. So that's one thing you're going to really want to be careful of. If I was you, I would use the copy and paste method. Please, please, please use the copy and paste method. Start on a Google Doc. Make sure that you have your ID number, your AP ID number up at the top, as well as your initials, okay? So my number might be like 68A342 and my initials. And then from there, I'm going to put question 1, letter A, and I'm going to type my answer in. When there's 5 minutes left, it'll tell you immediately stop mid-sentence, copy what you have, and paste it into the test. That's probably going to be your best bet. If you want to, in your Google Doc or on Word, download it as a PDF and upload it, that's absolutely fine. You can try to do that. I've had, some of my students have had issues with that on the Monday AP Physics C exam. Best thing to do is copy and paste. All right, so going back to that strategy again. This also kind of answers, somebody wanted to know about energy. It was the second highest in terms of votes. So let's think about 99% of the time, you can answer a lot of these questions just using energy. So let's think about the types of energy that are here. We know that we have potential energy due to gravity at the very top. Down at the bottom, we actually have a couple different types of energy. One of those types of energy is going to be kinetic energy that is translational, because the center of mass of this object will travel straight down the incline. And so that is a linear kinetic energy. But on top of it, I'm also going to have rotational kinetic energy. So when they want me to state how would I try to find the final velocity of the ball at the bottom, I would first state I would find the potential energy due to gravity. So that is UG, and that's equal to the mass of the ball times gravity times our height. And you'll notice I'm using the same abbreviations I did there. Then I would say that that is converted. Now I'm writing all this out. I'm not just writing equations. I'm actually physically typing these things. So potential energy due to gravity, which is the mass of the ball times gravitational acceleration times the height of the incline, that energy will be converted into both translational kinetic energy, which is 1/2 mv squared for the ball, plus rotational kinetic energy, which is 1/2 I omega squared. So now you have to say you also need the radius of the ball in order to find the rotational inertia. And they might even say, you know what the rotational inertia is of the ball. And that would be easy then to just say it needs to be in this equation. From there, you would say, I would make sure that I convert the rotational form of velocity into the linear form. So remember, our equation to go between the two is your linear thing or your translational thing is equal to your rotational thing times the radius. So this is equal to omega times r. And so here, if I want to know what v is, I have to take v, I have to take omega times r to get v. Okay, so I would multiply this. Then I'd go through cite evidence, tell, kind of where it's going through, and then give a good explanation of my answer. So that's one strategy. The two types of questions we're going to have are going to be qualitative, quantitative translations. So that's question 1. That's worth 60% of the exam. And the things you need to think about for a qualitative, quantitative translation. I'm going to show you, I've got a really good, little Google thing that is going to show you kind of what to do for these. So I'm going to pull it up really quick here. Here it is. And we'll put it on the screen. And I just want to go through and show you, since this question, so this type of question is the one that is worth the most points, let's spend a little bit of time kind of dissecting one of these. If we want to list some qualitative features of this rocket, we would do anything that wouldn't involve a number. So we don't want to worry about its size. We could say that it is reusable. We could say that the color of the outside is white. We could say that it's very large if you want to. So those are qualitative. Quantitative would be all the number items that you see here. So a qualitative quantitative translation is a question where you're going to feel like you're answering the same thing over and over and over again. So why is that? Well, here's why. You might be given a graph. And then in that graph, they're going to say, okay, we want you to take a look at this graph and tell us, what does the graph, and I'm going to move this over here for just a second. They might say, what exactly does the graph show you? Okay. Or what does the graph tell you about this object? So let's go ahead and kind of do that to the side with a graph. So I'm going to move that over, and then I'm going to move this over a little bit. All right, here we go. So there might be a graph on the exam. So I guarantee you're going to see a graph at some point. I've not seen the test, but we've done enough of these that I'm almost 100% sure you're going to see it. So here we go. So let's go ahead and we're going to draw a graph. So here's our graph. And this one actually suggests that we take a look at, here, I'm going to move this guy over. Let's make it a little bit small so that we can see it a little bit better. All right, so that might be a little bit too small, so we can make it a little bit bigger here. So let's zoom it up just a little bit. Zoom out. Oop, nope, zoom in, sorry. So we're going to zoom it in just a little bit. There we go. So that's going to be a lot better. All right, so they're going to do maybe a graph of force versus distance. So here we go. We have force and we have distance, and they're going to give you that graph, okay? And they will ask you how, not what is the value, but they're going to ask you, how would you determine, and I'm just going to state the rest of it. How would you determine the amount of work done? How would you determine the amount of work done? So at this point, your basic physics would be the area under the force versus distance curve is going to give me the value for work, okay? So how would you find the amount of work done? Then I'm going to cite evidence. Looking at the graph, I could find the area of the triangle, and then I'm going to draw it together. The area of the triangle represents the amount of work done, since it is the force times distance for the graph. So we've done that. Then they would say, how does the motion diagram, so we're going to look at a motion diagram here, how does the motion diagram relate to the graph? So a motion diagram typically has several dots. So you'll have a dot here, and then you would have another dot here, and then a dot a little bit further out, and then a dot a lot further out. Each one of these dots represents both a position and a time. They are sequential times. So this would be 1 second, 2 seconds, 3 seconds, and 4 seconds. And this would be different positions. And notice that you're getting further and further apart. If I put arrows here, the arrows represent the speed of the object, and this is going to go off the page, the speed of the object at different times. So now I can say The graph is showing that the force is increasing per unit time, and therefore our acceleration is also getting bigger. So not only is this thing have a bigger velocity, it also has an increasing acceleration. Then they would say something to the extent of, hey, here's a free body diagram that a student drew for that. Remember, the first question we looked at was a ball on an incline. And this is what they would do. They would say, here is what the student drew. And what we would like for you to do is go through and tell what is correct or what is incorrect about this diagram. So for this diagram, what you would do is you would have to write basic physics, and you should say something about the normal force is perpendicular to the surface. And then at that point, you could cite evidence and say the normal force is not perpendicular to the surface in this, and then draw it together and then answer the question. Therefore, the normal force needs to be erased and redrawn so that it is at a 90-degree angle or perpendicular to the surface. So that is a pretty important little piece right there. So hopefully that helps a little bit. They might also ask you about energy momentum. So they might do bar charts or graphs or something like a pie graph. The most popular way to talk about energy is to use an LOL chart. So this is LOL. And let's go back to our ball, okay, over here. And it rolls down the incline. Remember, we had our height h. We're relating this all back to energy again, so hopefully that's helpful. We know the ball translates and it rotates on the way down. And so they want us to just talk about what this diagram should look like. So remember, in these LOL charts, you have potential energy due to gravity. You could have spring energy, and then you could have kinetic energy. So for this one, we're going to have kinetic translational and kinetic rotational energy. So I'm going to put both those in. This circle is reserved for talking about what the system is. And so let's say that we only include the ball in the system. So we just say in the system is just the ball. That leaves outside the system the earth and the ramp. So at this point, the ball's not moving at the top. And because we're not worried about the earth or the ramp, just the ball, it doesn't have any energy at all. And then suddenly over here, it still doesn't have any potential gravity, doesn't have any spring energy, but all of a sudden it does have some kinetic rotational and kinetic translational. And so we're just going to put a couple bars there. They might say a student drew this. Comment, is it correct or not correct? Then they might change the situation. They might say, well, now the earth is in the system. So if we add the earth to the system, we can now say that it starts with potential energy due to gravity. And then that energy is transferred into translational and rotational motion. The only problem is we have a little trouble with rotational if there's no ramp because there's nothing to get it spinning. So now if we add that ramp, now we can have the whole system all together. So in a qualitative quantitative translation that you'll do on the first part of the exam, you're going to see multiple representations. And it's probably going to be for the same scenario. And so you're going to have to be able to use a graph to describe something. So if we think about work, we could do a force distance graph. For motion, we could show a accelerated object. For the free body diagram or extended free body diagram, we did that. And then if you need to, they could do rotation. We could do energy and momentum using bar charts and things. So hopefully that's super helpful and you will see that. Other things that you might need to do on a qualitative quantitative translation, which is that first question, is give a qualitative words-only explanation of how you got your prediction. They will definitely do that on this one. If not, they will give some student, and they might even say 3 students are debating what's happening in the system. Student A says this, student B says this, and student C says this. Pick one of the students and describe why they are correct. So if we go back to this little system here, we could have one student say, well, it just has translational kinetic energy in the end, and there's work that goes into the system. And so they would want to know, what does the system compose of? Well, it's just the ball, just the ball. And then if we say, well, now there's Jimmy, the second person says, well, there's potential energy due to gravity at the beginning, and then just translational down at the bottom, then we would know it's both the ball and the earth. And then finally, Susie, she's the last person, says, well, there's got to be rotational energy in the end. So now we can put that ramp in, something for the ball to rotate with. So hopefully that makes sense, that you're going to need to do a qualitative, quantitative translation. The big thing that you're going to see here is derive equation. If you have to do any equation derivation, it's going to be super simple. It won't be much. They have told us they're trying to stay away from deriving full equations. And that kind of takes us into when you need to type an equation that typically has a subscript or a superscript. So one of the things that you can do, so for example, let's say I'm talking about translational kinetic and rotational kinetic energy, and we're talking about gravitational. So I could say UG then is made to go into, or it's conserved, and it makes rotational kinetic energy. So I could put Kr or K little r plus Kt, which is translational kinetic energy. So that's a good way to do it. If you needed to type in the letters to explain each one, it'd be MGH is equal to 1/2 MV caret top 2 plus, and then rotational, well, that's really translational. So let's switch that. That's translational. This one is rotational. And this one would be 1/2 I, and then omega, you can just put a W and put a square. You do not have to change these, okay? So as long as it's something that seems to be about the same, use it. If not, look and see what directions they give you. So that should be super helpful. The other thing they said here is evaluate an equation for reasonableness or plausibility. So what we've typically seen them do on the exam when they do this is they might have an equation that they have taken something from. So for example, let's just use our kinetic energy, translational kinetic energy. So K is equal to 1/2 mv squared. And we know that potential energy is equal to mgh. So if I set the two equal to each other, let's say I want to solve for h. If I set them equal to each other and then solve, h would be equal to, and then I would have the 1/2 mv squared, and then I'd have to divide that by m and divide it by g. So they would say, is this a plausible way of solving for the height of the ramp if you know the mass of the ball, the speed of the ball, and the value due to gravity? And then that would be the correct way. But they might do this. They might say, well, a student comes up with the following equation: 1/2 v squared times g. What's wrong with this equation? So why does this equation not work for this scenario? And you're going to need to say one thing. The g should be on the bottom. The m's, notice they're both for the ball, and so they actually cross off. So mass, everybody bought mass to the party, so you don't have to have it. So it's not there. So that's the only thing that's wrong with this equation. So you would say, due to conservation, your basic physics would be energy is conserved in this situation. And so if we don't worry about the rotation of the ball, we could say UG is going into kinetic energy. Cite evidence. You could go through and then give the equation. So MGH is equal to 1/2 mv squared. If I cross off my m's, and you have to verbally or type everything out, then I should end up with height is equal to 1/2 of v squared times g. So that's the, 1/2 of v squared over g. Therefore, the student is wrong, but that's kind of what they're going to do. Okay, so hopefully that makes sense for a qualitative quantitative translation. I'm going to go back to just using OneNote again here so I can draw some things. And I'm going to pull up, we had a lot of other things in terms of questions. So let's pull up some things that we have here. And I'm going to update this little guy here. And let's take a look at the number of votes for these. So I'm going to go back one more time and take a look. So I'm actually looking to see for the Cram finale what it is you guys really want to know. And so let's go back a couple slides here. Sorry about this. Okay, so that looks good. Key topics we need to review. I think we already kind of went through that. I see there's a question about moment of inertia. It looks like it was answered by Mr. Peter Apps, which is awesome. So that one should be good. And angular momentum. Let's do this. I think this will be super helpful. I'm going to turn on the chat, which is always dangerous. And then what I'd like for you to do is go ahead and type in a question if you have one. Let's look and see maybe what you have. And before I do that, I'm going to check something here really quick. Yeah, I think we're good. Oh, boom. Okay. All right. Okay, cool. Awesome. All right, here we go. I'm going to open up the chat. I got to get over to the chat. So I'm going to open the chat. If you have a question, go ahead and type your question. I'm going to give you about 15 seconds, and then we'll go through the chat, and I can kind of see what it is that you want to know. All right, here we go. All right, I think I got it. Yep, let's do that. Okay, so I see a lot of questions about simple harmonic motion. So let's do some stuff on simple harmonic motion. And what we'll do is we're going to do simple harmonic motion. And so, all right, cool. All right. The simple harmonic motion, here we go. We know that for simple harmonic motion, SHM, the thing that they're going to probably do is they're going to ask you about energy for simple harmonic motion. So let's do this a couple of different ways. And I think that'll be super duper helpful. And if it's not, I'm really sorry, but I think this will be super helpful. So what I'm going to do is I'm going to draw, I'm going to actually make this a lot smaller. So I'm going to draw it's still really big. So let's pull this down really small. Oh, I see what I did. All right, here we go. So let's draw a table. And on that table, we have a little stand here. And then attached to it is a spring. And then there's a block attached to that spring. And you reach out and you grab that block, okay? And we're going to say this is our equilibrium position. This is our zero position. And when we pull it, we're going to pull it in this direction, and we are going to have it at this point. This is our positive. Over on this side, we're going to have our negative position, which means that when I let go of this now, it's going to slide back. It's going to go past this point, and then it's going to end up here, and the spring will be then really compressed. Then it'll push it back. And we're going to say that there is no friction here at all, okay? So no friction. Tell me, let's think about the energy that we have at position 0, at position plus, and the type of energy we have at the minus position. So let's start this first with the positive position. Go ahead and tell me what kind of energy does it have at the positive position? What energy does it have at the positive position? Go. Be more specific than potential. Very good. All right, so I'm seeing it. So that is correct. At this position, it has all spring potential energy. At this position, it also has all spring potential energy. And then at this position, it's all kinetic energy. So I know that it is oscillating between the different types of energy. So here's the next thing we're going to do. We're going to create a position. Okay, so this is a x position versus time graph. And when we do that, this is the positive, this is 0, and this is negative. We pulled it over to the right. So now we're going to have this position. Then it accelerated, okay? So when it accelerated to the left. When something accelerates to the left, okay, it has negative acceleration, which means that this should curve down like this. Now we have all kinetic energy, but it keeps going left and it starts to slow down. And so we end up with a curve that looks like this. So here is your simple harmonic motion curve for this block as it starts. And what we'll do is we'll number these. Starts here, and then it goes over to number 2, and then it goes over to number 3. So this is 1, 2, 3. Then it makes its way back. We're going to call this position 4. And then finally it ends up at the beginning, which is position 5. So now we've gone through and we've hit all of those positions. If you think about earlier, we talked about the equation x is equal to a times the cosine of 2 pi ft. We know our times, okay? So this is 0 time, so we're just going to call this 0 time. We're going to call this time 1, time 2, times 3, and time 4. So let's do those in a different color. Let's do blue. So 0, 1, 2, 3, and 4. Okay, cool. So what is the A in this? The A is the amplitude. So that is how far we stretch it. So from here to here is also the amplitude. So now you see it on the graph and you see it here. But remember, there is also amplitude here, and it is exactly the same. So the two amplitudes here are exactly the same as long as there is no friction. All right, I'm going to pause for just a second. I have a quick question. Is this helpful? So is this helpful what we're doing right now? Does this make sense? Is this helpful? Chat is on. If you want to let me know, is this helpful? Yes? Okay, cool. All right, we will keep doing that. Yeah, so, and I know you have lots of questions, but we've got 260 people, so I can't answer them all, but we'll keep doing this. All right, A is our amplitude. Our frequency, remember, is how many of these things go by every second. So notice that because this is 1 second right here, we have a quarter wave. So our frequency here is you have 0.25 every second. So now what we can do is if we gave this a value, I know we could say it's 1, we could actually find the position. And so what I could do now is I could plug in my time of 0, and I should come up with, when I do all my math, the position up here of positive. If I plug it in and my time now is 2 seconds, then I would end up with a negative position. But that's kind of how that works. So let's do the next thing. So let's look at what happens when we go from position time to velocity time. If you are a calculus student, the cool thing about this is you can think about plus, minus, minus, plus, and then CS, CS. Okay? And here's what we're going to do. we started with positive cosine. Notice there's no negative sign there. So this represents our position versus time graph. Then we're going to go to the very next thing. And so if we look, this graph starts right here. And so this is a positive cosine graph, which is really cool. Then if I want to know what the velocity versus time is, if you're a calculus student, you know what I'm doing. I'm doing derivatives. But don't tell anybody that because you don't need to know that. But if I now want to know what is the velocity versus time graph, watch this. I'm going to find the slope of the line, of the curve, so the tangent line here. And I notice that, remember, the slope of position versus time is velocity. And because it's a straight line, it's actually 0. Now I'm going to go to number 2, and I'm going to draw a straight line. This line, the slope, is velocity, and notice it's negative velocity. So for position 1, I have a negative velocity. At position 3, notice I have a velocity equal to 0. So I'm going to put that right here. At number 4, tangent line would be very positive, so I have a positive velocity. And then at number 5, I have 0 velocity again. Now I can draw my curve. So now I have this wave. And if you notice, it starts at the middle and moves down. So that now gives me the negative sine graph. So what would happen if I kept going? Well, we could keep going and we could say, hey, let's find out what is the acceleration versus time going to look like. We're going to do the same thing. Here it's very negative. Here it's 0. Here it's positive. Here it's 0. And here it is big time negative again. And what do you notice about acceleration versus time and position versus time? They're just inverse of each other, so they're upside down. On the test, I think the big thing they're going to do is they're going to ask you what would maybe the graph look like for the energy as you go through. So let's do kinetic energy. Which of these graphs is kinetic energy most related to? Position time, velocity time, or acceleration time? Well, we know kinetic energy is going to be related directly to your velocity. So if we don't have any velocity, you will not have any kinetic energy. So we're going to put a dot right here. If I have negative velocity, do I have negative kinetic energy? Well, remember, kinetic energy is 1/2 mv squared. And so no, it won't be negative kinetic energy. It's actually going to be positive kinetic energy. Then I get back to here, no velocity, no kinetic energy, positive velocity, positive kinetic energy, and then none. So now I can draw my graph and it should look like this. So that's for kinetic energy. How about potential energy of the spring? Well, remember we said that it has lots of potential energy at the edges and no potential energy for the spring in the middle. So I want to relate it to this graph, the position graph, because the position graph, when it's way positive, it has a lot of energy, and way negative has a lot of energy. So we're going to do the same thing. So this is the potential energy of a spring. When I started, I had lots of spring energy. When I got to the middle, so when I got to position 1, I don't have any spring energy. And then when I get here, I don't have negative spring energy. Why? Because remember, the potential energy of a spring is equal to 1/2 kx squared. So even though my position is negative, I square that, and that gives me a positive spring energy. And then it goes back to 0, and it goes positive again. So now we can draw our graph and show those energies as they go through. And you'll notice that when this one's going down, this one's going up. So if you add the two energies together and we think about total mechanical energy, so I'm going to put TME, that's total mechanical energy. If I add this graph and this graph, it should give me a straight line. That proves that my total mechanical energy behaves in a way that we have conservation, of energy. Okay, so now we have conservation of energy. That's how you would do this with a block on a surface with no friction. Could we also do the same thing with a pendulum? And so notice this is going to be the exact type of thing. We're going to draw this little number line here. We're going to put positive, 0, and negative position. Notice this is no different here and here. But instead of spring energy, we have potential energy due to gravity. Here, we have kinetic energy only. And here, we have potential energy due to gravity again. So notice it's not really any different for simple harmonic motion. Once you understand one, you should be able to understand the other. So hopefully that was somewhat helpful and didn't really confuse you too badly. All right, tell me, what? Yeah. So somebody asked, can we do the same thing with an object hanging? Absolutely. All right, cool. Yeah, kinematics you should know. All right. Yeah, F is frequency. Okay, what do you want to do on rotational motion? What do you want to do on rotational motion? What do you want to do on rotational motion? So let's see. Diggy, 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 diggy. Yeah, all right. So I think I have some ideas just kind of looking at some of the serious comments that are here. Yeah, let's do a little bit of torque. All right, here we go. I'm going to disable the chat. All right, so I'm going to scroll this guy down a little bit. Let's talk about torque. So we have a really cool little system. What we have is we have this object, and it looks like this. And this object can spin in a circle. So this can go this way. This can go this way. This is kind of like a tube. And then we're going to put two really heavy masses on each side. This is on a table, and there's a stand here, and it can rotate in a circle. And so that works out really well. And I'm going to check something here really quick. Okay, cool. So now what we're going to do is we're going to take a string, and we're going to tie, oops, I want that string to be green. We're going to tie the string around here so it loops its way around. And this whole thing is sitting on a table. Okay, there's a pulley here. And that pulley, the string comes down over the pulley, and then we have a mass here. We're going to call this mass M. So here's kind of the cool thing that we can do. We know if we think about force, we have a force pointing down, and that force is mg for this block. So we're going to put mbg. And then up, we also have a force, and that is the force of tension. We have a force of tension down. We have a force of tension to the left. And we have a force of tension to the right. Okay. Now, if we take a picture of where the string is wound and blow it up, here's what we're going to see. We're going to have our bar. So we're looking from the top down. So we're looking from the top down, and we've got our string, and it's wound around this guy like this, and then it comes off, and then it goes over to this pulley. And so the cool thing we need to do here is we need to look at several things. One of them is the radius here. And remember, we said that we have a force that is acting on the string in this direction. We call that the force of tension. So here's what we're going to do. We need to figure out what is the acceleration of this system. I want to know what is the angular acceleration. So what is the angular acceleration of the system? How would you find the angular acceleration of this thing as it rotates? Okay, so let's do this. We know we need to start with the sum of the torques. And the sum of the torques is equal to I times, and then anybody, Does anybody know? Well, let's make sure that we can look at our equation sheet. So remember, if you're not sure, go to your equation sheet. Let's look for torque. Here's one torque, but that's not what we want. We want this torque. So it's actually I times alpha. So we're going to move this back down. So this is I times alpha. So there's your I times alpha. Do we know the moment of inertia of this? Well, sure. If I know that this is big M and this is big M, and we have a radius here, we could actually find the moment of inertia for it. And then the other question is, do we know what the torque is that's pulling on the little pole? Remember, torque is also equal to the force perpendicular to the radius. So as long as it's at 90 degrees, we can just write the equation like this. We don't have to use sine or cosine or anything like that. So now I know I have an equation, force perpendicular to the radius is equal to I for our system times the acceleration of our system. But what's the force that's pulling on it? Well, let's take a look at the sum of the forces. And we know this thing is accelerating, so that's equal to m times a. If we look down at the bottom, and we're going to say down is positive, we have mBg. So that's mBg, okay, minus ft plus ft minus ft plus ft. Oh, so those go away. And so now I have mass of the system times the acceleration. I can now solve for the acceleration. I can do some other things, and that will help me then find out what the force is that's pulling on it, as well as we know the moment of inertia and the radius, so now we can find the alpha. They're probably not going to do anything that complicated. They're probably going to do something a little bit easier. They might talk about conservation of angular momentum. I think the big thing that you need to do here is remember there are two equations for L, two equations for angular momentum. So let's go back to the equation sheet really quick and look at both of those. One of them is I times omega. The other equation is the change in the angular momentum is equal to the torque times the time. But there's one more. So I would write this one in. L is equal to, so remember, we know that, for example, if I want position, I just take my rotational thing times r. So if I want, instead of using I omega, I can actually use mass instead of rotational inertia. And then instead of using velocity for momentum, I can use, instead of using the omega, I can use velocity times radius. So this is the other equation that might be super important for you to have that is not on your equation sheet. So be really careful with it. Because it can be used in conjunction with all of these. So if you are conserving momentum and you have something moving in a straight line and then it bumps into something that is rotating, you can do conservation momentum that way. All right, so what we're going to do is we've got about 7 minutes. And I would love to help you make sure that you're ready when you log on to this test. So here's the next thing that we're going to do. If you don't mind, I'm going to pull up a Google Doc, okay? And I want you to either get a Google Doc ready to go, or I'm going to have you pull up Microsoft Word, and I want you to do the following things on the document, because this is going to be super helpful for you. So I'm going to give you just a little while. I'm going to give you about 30 more seconds or so, and I'll keep talking a little bit about the test. Don't freak out when you start the test. You definitely need to log on by 3:30. So in 6 minutes, we're going to stop and we're going to get you started, okay? We want you to get your stuff ready. Maybe you go to the bathroom, take a break, get something to drink, something to eat really quick. Make sure that your study space is quiet. Make sure your computer's on and ready to go. One of the things that you want to make sure you do is up here, I have a little program and it's called Grammarly. If you have Grammarly, you need to turn it off. You need to go ahead and either, at this point, I would just remove it from Chrome altogether, okay? You can manage the extension. You could go in and you could turn Grammarly off. That's the other thing to do. So I'm going to turn my Grammarly completely off. You want to turn off any extensions that you have. You probably want to turn those off, okay? So like I've got Amazon Assistant. So I'm going to go in and I'm going to turn off Amazon Assistant. The reason they want you to turn these off is because some of them might interfere with your test. The one that they are the most worried about is Grammarly. But remember, when you're done, it's super easy. You can go back into your extensions and you can re-enable those. So I've got all these extensions. You can actually just go to your extensions page and just turn them off right there, okay? So that's an important thing to do. Now that I've turned it off and I think you're ready, what I'd like for you to do is I want you to type your AP ID number. So your AP ID number, so your actual number, and then hit the tab key a couple of times and type your initials. So I just typed mine. At that point, I would type question 1, and then there are supposed to be several parts to these. I would go ahead and put A, put a B, and put a C. And then if there are like part AI or part AII or part AIII, you already have this set up and ready to go, okay? So please, 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 I would do that for the first one. And then where you have your name for your document, you might just save it so that you know that it's question 1. So then I just put Q1. Once you have question 1, go to File, make a copy, and do question 2. So you've already got everything filled out. You just need to change it to Q2. So now I have question up, ready to go. Question 2, I just need to change this one thing to 2. Now you're ready to take the exam in terms of your 2 question docs. So in another tab, you're going to want to go into where the test is. If you're not sure, look at your ticket. You can also type in AP Physics 1 2020 exam, okay? And then they're going to have some questions there. You could actually go in. Here's AP Central. You should have the address as to where you need to go for that exam, okay? And so I think that would be super duper important. Now I've got both my question things ready. The other things that you might want to pull up are any PDFs you have that might be useful. And then make sure that you have printed the AP Physics 1 equation sheet. If you have not, if you go to Google and just type in AP Physics 1 equation sheet and hit enter, it's the first thing. It is a PDF. I would download that PDF to your desktop, and then I would show it in your folder, and then I would 100% open it in Adobe Reader. And that way you won't, if you close it, if you accidentally totally close it, you won't close your exam also. The other thing that a lot of us are telling our students is once you get the test open, let's say that this is the test, then I would split the page so that on the right side, you have your place where you're answering. And on your left side, you have the actual exam itself. When you're done typing, just copy this and you'll paste it right into your answers. I would say that's probably the best way to do this, okay? So here's what I'm going to do. I'm going to turn on the chat for the last 2 minutes. I'm going to let you go ahead and ask any questions you want to. Other than that, I think that's it. So you guys should be good. I know I see a lot of momentum and pendulum. That was an AP Physics C question, so it probably won't be on this test. All right. I think you guys are going to be good. I really, really do. Yeah. So things that you need to type that are, Greek symbols, you won't have it. They're going to give you things. Don't worry about banking angles. They probably aren't going to ask anything about it. Linear momentum and angular momentum are both conserved as long as there's nothing in terms of outside forces acting on it. Okay. If you go to those resources, download them. You do not want to be on Discord because if they catch you on Discord copying and pasting, you will not do well. Download the sources that you need. Take your time. Oh, pacing advice. Watch the timer. You're not going to get done. It's okay. Okay. Definitely, as Fiveable is telling you, stay off Discord. Stay off shared Google Docs. Please, please, please do that. You guys are 100% awesome. Thank you all for showing up today. You will do awesome on this test. Keep your head up. Answer the best you can. Don't worry about things that you can't answer. Just go ahead and ignore those and move your way through the exam. Hey, good luck, guys. This test should be super doable. Take your time. Make sure you upload when it says upload now. Don't wait till the end of the 5 minutes. Do it immediately. Okay. You can also upload early if you get done early. You can do that. You probably won't get done early, but you sure can. All right, guys. Thank you so much. Talk to you later. See ya.